Okay, so last time we introduced our concept of the axial normal stress, sigma is equal to the force divided by the cross-sectional area of a specimen. There are a couple terms that we need to talk about associated with stresses, and one of them is a stress distribution. Basically, a stress distribution is just a sketch or a picture of how stress acts on an area. For our bar in axial tension, you can show this pretty straightforwardly. If we show a force on this side, then the stress distribution on a side view would be little stress arrows spread out over that cross-sectional area. Let me see if I can make a 3D perspective view of the same thing. If we look at our round bar, it has some sort of round cross-section. Here's my axial force. Then the stress distribution would take a shape that would be a cylindrical shape. On that cross-section. And you can take a look in the book and you can see different types of stress distributions. Basically, it's just a picture of how that stress acts on the cross-section. There are a couple terms associated with stress distribution. You can have what's known as a uniform stress distribution. A uniform stress distribution is if the stresses are all at the same value everywhere on that area. And then a non-uniform stress distribution is if the values of the stress change at different locations on the cross-section. All right. Now, when we use the formula sigma is equal to F over A, we assume that we end up with a uniform stress distribution. And this is as long as that axial force goes through the centroid of the cross-section or the centroid of all the cross-sections that go down the axis of the bar. Give an example of a changing cross-section, but still an axial stress distribution, uniform stress distribution. So if we have a small diameter on one side and a larger diameter on the other side, and the bar tapers what we call smoothly from one end to the other, then we can imagine there's an axis that goes down the bar, and this dotted line would go through the centroid of each of those cross sections. If we apply an axial force, and the resultant axial force goes through the centroid on the other side, then we still end up with a uniform stress distribution on any particular cross section down the length. Now there's another word that I just used, and that is resultant force. And so let's talk about that one in a little bit more detail too. We're going to define the resultant force as the volume of the stress distribution. So if we look at our previous example of a round bar with an axial force on it, we get this stress distribution, sigma, that has the same height everywhere. We have the area of the cross-section that we would know. And if you notice, that stress distribution in this picture takes the shape of a cylinder. The volume of a cylinder, in our example, is the area of the base times the height of the cylinder. For the stress distribution, this is the area of the cross-section times the value of the stress, sigma. And if you notice, this resultant force is just rearranging the formula. Sigma is equal to force over the area of the cross-section. Now, this rearranging this formula works if you have a uniform stress distribution. If you do not have a uniform stress distribution, the resultant force is still the volume of the stress distribution, but you may have to use some more sophisticated ways in order to figure out what the volume of the stress distribution is. You may have to use calculus. You may have to do an integral. You might recall that if you have some sort of surface that changed from one position to another, I'm just making some squiggles here to kind of show some different values of stress. So maybe it's high on some sides and lower on the others. It's kind of dipping up and down over here. Well, if this is a stress distribution that is non-uniform, the way that we can find the volume underneath this shape is to do an integral over the area of that base of the value of the stress at any particular point. Could be a function of, say, y and z, if x is down the axis of the bar, dA. And we'll actually do this a little bit later in the class to find some resultant forces using calculus. For right now, just remember that the resultant force is the volume of a stress distribution. All right, well, let's get to our next concept, the concept of strain. Strain is related to stretching or deformation in a material. Let's kind of step back for a moment and talk about what happens when we put a load on a structure. When we load a structure, a couple of things can happen. The structure can move, or a point on the structure displaces, and or the structure can stretch out. So let's define displacement as the amount of movement of a point on the structure. We can have what's called rigid displacement if we take our structure, say our round bar, has a couple points we can identify on it, maybe point A on the left and point B on the right, and some length in between, L0. We can displace this just by picking it up and moving it to a new position. During that movement, we didn't stretch it out at all. And we have what's called rigid displacement. And one of the things that you might notice is we can even define rigid displacement as the displacement of a bar in which the distances between points do not change. So that's just another way to say the same thing. Let me give you a sketch of displacement with stretching. We can take our same bar. Here's point A and point B. And we can put some loads on it as well as picking it up and moving it. And move it over here. And exaggerate this deformation so we can see it easily. And my points A and B move and stretch out. You can have just stretching. You can have displacement due to just stretching if you fix one end of the bar and pull on the other end. In our class, we're mainly going to be interested in the stretching in the material. You take a whole nother class called dynamics where you talk about the displacement of rigid bodies. We're going to find a term now called strain. As the change in length of the bar divided by the initial length. So this bar used to be L0, now it's LF. The change in length of the bar is the final minus the initial length. And then we can calculate kind of a percentage, almost, as change in length divided by the original length. If this was a percentage calculation, we'd put times 100 here. But what we're going to do is we're going to define this as the Greek letter epsilon as the axial normal strain. All right, axial normal strain has a sign associated with it, just like similar to what stress does. But we can take a look at this formula, epsilon is equal to delta L over L naught, and look at that. And if the change in length, the portion on the top is greater than 0, if it stretches out, then the strain is positive. But if the bar gets shorter, if delta L is less than 0, then the strain is negative. We can also look at the units of strain. Like a percentage, there is no units associated with this. You can have inches per inch, which cancel out to give you no units. So strain is a unitless measure. So let's put that in here as a note. All right, so let's do an example where we use this idea of the extensional strain. Suppose we have a bar, that's a pretty crude sketch of a test specimen, and it's got a 12-inch gauge length before any load's applied to it. And after the load's applied, it stretches out. I'm exaggerating this deformation, but it has a new length of 12.01 inches. So to calculate the extensional strain, we need to find the change in length, and the change in length is the final minus the initial length. We can do that pretty easily. It stretched out to 12.01 inches. The initial length was 12.0 inches. So we take the difference to get the change in length. And then compute the strain by this change in length over the initial length of that gauge section. The number that we get in this case is a pretty small number, 0.000833. Some people will use the units of inches per inch when they write this down. Some people will just write this as a unitless measure because it is. So they write down 0.000833. If you have your calculator in engineering notation, what you would see would be 833 times 10 to the minus 6, to 3 significant digits. And if you remember what we talked about last time, our symbol for 10 to the minus 6 is mu for micro. So then we'll write down 833 micro. So what you might see in different books is 833 micro. You read that as micro strain. Sometimes you will see this written again with units, 833 mu inch per inch or millimeter per millimeter. Now, one thing I want to point out about extensional strain for most metals is they tend to be fairly small values. It's something times 10 to the minus 6, something times 10 to the minus 3. It's very typical of things like steels and aluminums, a lot of different engineering materials. And the reason why they're very small numbers is if the numbers get very big, the material will break before it has that much strain. All right, well, loads are not the only way that we can get strains in structures. We can also get strains from temperature changes. So to give an example, suppose we have our bar, our tensile specimen with some initial length at room temperature, and then we take that same bar and we put it in a furnace over here, and we heat it up and we increase the temperature to some temperature T, and we have a change in temperature that's greater than 0. Most materials, when you heat them up, will expand, and the bar will have its new length of L0 plus delta L. We can calculate strain just like we did before as the change in length divided by the initial length. But when this is due to temperature changes, this is known as a thermal strain. We can make a plot of strain versus the change in temperature. As the temperature increases, the strain will increase. For a lot of materials, this is basically a straight line relationship for a certain portion of their temperature behavior. And the slope of this line is associated with something called the coefficient of thermal expansion, alpha. And so what this says is that the strain due to a change in temperature, or the thermal strain, is equal to the coefficient of thermal expansion times the change in temperature. Thermal strain is also unitless, so while change in temperature may have units of degrees Celsius or degrees Fahrenheit, make this a unitless quantity for strain, the coefficient of thermal expansion will have units of 1 over temperature. Right, to give you an idea of what the coefficient of thermal expansion is for a material like steel, alpha is 8 times 10 to the minus 6 per degree Fahrenheit at room temperature. So if you increase your steel by 1 degree Fahrenheit, you have 8 microstrain that are induced just due to that thermal expansion if the material is free to expand. We're going to do an example next of thermal strain. All right, so I've had the good fortune to work a little bit with the power generation industry. And I've gone out to see one of these power plants, a coal-fired power plant. It's very impressive. Where they actually generate the heat to heat up the water in the boiler tubes is what they call a room with a tube wall. So all along the wall of this giant room are these pipes filled with water under high pressure. What they do is they take coal, they pulverize it, shoot it out in space in the middle of this room and ignite it, and this just continuously burns in this room. And while coal will burn somewhere around 2,000 degrees Fahrenheit, you have some energy losses. By the time you get to looking at a boiler tube itself, the surface of the boiler tube may get to be a change in temperature of about 1,000 degrees Fahrenheit. So for our example, let's take a look at a boiler tube wall pipe in a power plant. Has an initial length. Now, these are very tall buildings, about 15 stories tall. So let's just say it's about 150 feet tall. And with a change in temperature, we'll assume that it's a uniform temperature change of 1,000 degrees Fahrenheit. What we want to do is we want to calculate what the change in length of the boiler tube pipe is. So we're going to use our idea of thermal strain. The thermal strain is the coefficient of thermal expansion times the change in temperature. And we also know that that's going to be equal to the change in length divided by the initial length of this bar. We're neglecting any other sources of load on this structure right now. So if we want to solve for the change in length is equal to coefficient of thermal expansion times the temperature change times the original length. I'm going to put these terms in here now. 8 times 10 to the minus 6 per degree Fahrenheit. The change in temperature of 1,000 degrees Fahrenheit and an initial length of 150 feet. If we put all these together, we end up with a value of 1.2 feet for the change in length of the boiler tube. Now this is pretty impressive. So you start off with a coefficient of thermal expansion of only 8 times 10 to the minus 6 per degree Fahrenheit, 8 microstrain per degree change in temperature. But we have a pretty large change in temperature, 1,000 degrees, and we have a pretty long pipe to begin with, 150 feet. So we get a 1.2 foot expansion in the length of this pipe. Now if you're designing a boiler tube wall for a power plant, if you don't take into account the 1.2 foot growth in length of pipe as the thing heats up, you could be in big trouble because your pipe could expand and it could cover up ports that are in this tube wall, or it could go down and hit the bottom of the floor, and that would cause some problems. So thermal strain and change in length due to thermal deformation can be pretty significant in some instances. We're going to see later in the semester constrained thermal deformation can lead to some very high stresses. All right, that'll do it for this lecture. What we'll do on our next lecture is talk about stress and strain diagrams.